books, workbook, physics, atoms, applications. Okie dokie. So this is what I'm thinking. This one won't take too long to do, and when we get finished, maybe we'll have a look at some exam questions on radiation. Since I think on Friday I won't have a revision class, instead I'll just have a normal class so we can finish the chapter. So we should have a little bit of time at the end to do some exam questions. Okay. Right. So this, if you want to write this down, this is applications. So what exactly is radiation good for? So radiation, good or bad for your health? Bad, quite bad. Quite bad indeed. But it's not all bad. Yes, it's bad for your health, but it has some applications. So I'm just going to look at some examples of what it's useful for. So there's no calculations here for this one. We're just looking at different applications we have for it. So the first one is in a smoke alarm. So let me explain this. Yeah, you all have a smoke alarm at home. In fact, there's some on the top of the room there. You see, up the top there? Yeah. So what's happening here? So if you look here, this is your battery, and the battery makes an electric field here between the two plates. Yeah, so there's an electric field here, and then here is something radioactive, and it's releasing alpha radiation. Alpha, okay? Now, you know from chemistry what's ionization called, or what is ionization? Release of electrons. So what happens here is when the alpha hits the air in the room, it ionizes the air we breathe. So, what happens when the air is ionized? An electron comes out. So, if an electron comes out here, which way will the electron move? It will go up and hit this plate. So, if you have an ammeter here to measure current, what will happen to the current? It will increase. So, you have a current here, and it says current is on. Now, when there's smoke in the room, like here, the alpha radiation cannot ionize the air because there's smoke in the air. It's not able to ionize it. So then what will happen to the current? It turns off. And then when the current turns off, then the alarm turns on. So this is how the smoke alarm works. And you see up the top, the radioactive material is something called americurium-241. It's on your periodic table. Now notice that the half-life is 400 years. So this means your smoke alarm, if you put a new battery in it, it should work for maybe at least 100 years. Okay? So the smoke alarm, the radiation in it is decaying very slowly. So it will last a long time. Okay? So for the exam, they only ask you about 2 applications. I'm going to do more than 2, but the 2 that they ask you is the first one I'm doing, which is this, and the last one I'll do. So they could ask you, the question might say, briefly explain how a smoke alarm works. And this is how it works. Yes? What's wrong with you? It's difficult to explain. Okay. The best way to explain this is first you draw a diagram. So you draw this. And then, before you draw, then you would say something like this. You would say, the alpha radiation ionizes the air, and these electrons increase the current. When smoke is in the alarm, the air cannot be ionized, the current decreases, and the alarm will turn on. What's so difficult about that? No. It's important that you explain it in your words so you can remember it. So why don't you try your best and then I will check it for you. But first you should draw a diagram like this. Yeah? Say that again? I don't think you will get full marks. I'm sorry you may need to use some words in the exam. Your English is good, right? No? How to draw smoke? Here, let me show you how to draw smoke, like this. How you draw smoke. So I hope you can see with the first example, there's actually radioactive isotopes in day-to-day life. Like in this room, there's some radioactive isotopes in that smoke alarm and in that smoke alarm. So there, it's day-to-day as well. Louise, what did you write? Did you write something? What did you write? The explanation, did you write it? No. Who? Oh, Ibrahim? You're going to, right. Now hang on, before you write it, let's just make sure you understand. So Louise, can you explain to me how this works? Try your best.
When smoke goes inside for the alarm,
yes,
and the alphabet can't to put inside for the alarm.
Yeah,
which is the positive phrase.
Yes, you need the verb here. Yeah, it stops the ionization. You know this word?
Yes,
yeah. It stops the ionization between the negative and the positive plate. Yeah.
It's for the yellow.
Yeah, the yellow is the alpha. And it ionizes the air between the positive and the negative plate. And you're right, when the smoke is there, it can't ionize. So then what happens?
So we'll make the alarm turn off.
Turn on.
First turn on.
Yes.
No.
On.
Because
The current will turn off and the alarm will turn on.
Yes.
Yeah. Okay, that's good. That's good. Yeah. Who? You try now.
Okay.
Yeah, go on.
As we can figure it out.
Go on, try. Okay.
Radioactive or analyze the molecules in the air.
Yeah. You can even just say the air.
The air. Okay. And the electrons will be released off, and they will attract by the positive
Yes.
electron.
Yes. Positive plate.
Positive plate.
Yeah.
And the current vector turn on.
Turn on, yes.
Turn on.
And then smoke comes and
the smoke comes and the radioactive cannot with the air. So the current vector turns off and the alarm turns on.
full marks. It's not so difficult, is it?
No.
Will we go to the next example? Or do you want to write something down? I mean, I just think you can write some short notes to help you remember. You know, like bullet points. Here, look. So, for example, first point is the alpha ionize. How do you spell ionize? Ionize. Is that right? Ionize? I don't know. The alpha ionizes the air. And then the electron hits the positive plate. And then what happens to the current? The current turns on. Then what happens? The smoke can't be ionized. That means the electron does not hit the positive plate, and so the current is then off, and then the alarm is on. So this step here, this is the alarm is off, so you are safe here. And then here is not safe. Not so bad, is it? Okay, next example, next application. So here's my man here. And so you know a problem when you have pipes underground, you know, water pipes, gas pipes, whatever. Here water pipes. Sometimes they leak. There's a hole in them. And you have no way of knowing where this leak is because, you know, you can't see underground, you know. So what they do to find where the hole is in the water they put fluorine 18 in the water. Now you might say, oh, this is dangerous because then you drink it. But they only put a little bit. And the half-life is about 2 hours, which means after 8 hours there's only 12% left anyways. So if you do this, you know, if you turn the water off or something, or if you tell people don't drink the water tonight and you put it in the water and then the water becomes radioactive. And you walk above ground with the Geiger counter. Remember the Geiger counter? It does the click, 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 click sound. And then what will happen here is where the leak is, there's more radiation because there's more water. And it'll go click, 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 and he goes, the leak is here. And it's good, it's only 2 hours. So after 2 hours it's at 50%, and then 2 more hours it's at 25. 2 more hours, 12.5. So you see it quickly disappears. Yeah. So you can make a small note for this, but it's not on the exam. So just write for me 1 sentence. So, Ibrahim, how would you summarize this in 1 sentence?
Radioactive is used to detect radiation and was concentrated radiation.
Yes, and just also include that you put fluorine 18 into the water. So you'd say, a Geiger counter is used to find leaks in water pipes which have fluorine 18 in the water, or added to the water. Something like this. Something like this. It's important that you don't write what I say, because I'm not some genius. Yeah. So you just use your own words. Yeah, the man searches for the leak, or something like this. Like Google search. Same verb. Another thing to say about this, the radiation from the fluorine 18 is mostly gamma. This is also important. Why do you think it's important that the radiation is gamma? Mostly gamma. True, no, that's true. There's another reason too. There we go. The gamma can pass through the ground, but the alpha definitely won't, and the beta probably won't either. Only the gamma can travel through the Earth. So it just means in your sentence you can say, put gamma in front of the word radiation. So the man searches for the gamma radiation, something like this. Yeah, you got this? So what did you write, Who? Don't be shy. Yeah? Shall I ask Louise? Yeah. Okay, Louise, what did you write?
When we find
the leak, yeah?
The leak. When we find the leak for the water pipe, we can put the fluorine on the water pipe.
Yes.
And then after that, a man can search the gamma on the ground.
Yes, search for the gamma on the ground, yeah. So just say it's not on the pipe, it's in the pipe. Yeah. Good job, Louise. Okay, we go to the next example. Now this one, technetium 99M. These are difficult words. This one is used in hospitals, in the hospital. Technetium. Oh. This is used in hospitals. Now what they do here, I don't know if you ever done this, but they put this in your blood. Yes? They inject it inside you, and they can see where the radiation is. And I think for this person, I don't know, maybe this person has some problem here and here. because maybe, I don't know, maybe the person has some problems here. I'm not sure. I don't know how to read, I'm not a doctor, so I don't know how to see these pictures. But I'll give you an example, like, you know, if the person has maybe some kind of hole in their stomach, you know, maybe some blood is coming out, then they can see this because they can see it moving. You know what I mean? It's like an X-ray. You know, they can see inside you, but you know that X-ray, you can only use it for your bones. Whereas when you use radiation, you can use it for your blood and your skin. Yeah. And what's nice here is that there's not much alpha, so it's, you know, not too bad. And also the half-life is only 2 hours. Yeah. And also a lot of this radiation will go when the person goes to the toilet. So when they go to the toilet, the body tries to remove some of it. So of course it's not completely safe, but it's not too bad. If you use, you know, maybe like 1 gram, something like this. Anyways, you can say that this is used to find problems. It's used like an X-ray to see inside of people. Maybe I'll get Colin here for a second. Maybe you can help.
In favor of crossovers.
Should I be pointing out anything particularly wrong with this person, like something with their thyroid maybe?
What is this heat?
No, this is inject the radiation and away you go.
Okay. And a lot of the radiation has been injected into their blood. It's hanging around in the neck area.
Yeah.
There's some kind of lymph nodes down here under the arm, isn't it?
Yeah, that's what I'm wondering. Can you say, this person has...
No. A lot of it has been processed in the liver. A lot of it has gone to the lymph nodes. Technetium 99M after 2 hours.
Half-life is 2 hours.
Oh, sorry, 3 half. I thought the picture was taken 2 hours after. No. I don't know. I don't think so. It's nothing particularly obvious.
No? Okay. I didn't know if I could then say, you can see if there's something wrong with this.
Yeah. No, not necessarily, no.
That's all right.
No, he looks such overweight.
This is good for diagnosing hidden obesity, isn't it?
Sorry about that.
That's all right. I took you from your class. Thanks for that, though. Okay, so let's go.
He's very healthy.
Maybe he's healthy. Okay, we go to the next example. Yeah. Right. Now this example maybe you see at the airport. We can use gamma radiation from cobalt 60 to look inside of, cars, suitcases. Like here, for example, this truck we can see has some guns inside of it. Can you see that? This is a truck, and there's looks like 2 guns here or something. Maybe machine guns, yeah. So what's happening here is there's gamma radiation, and the gamma radiation goes in, like an X-ray, and it can scan inside of the truck. You see this at airports, with the machine for looking inside the people. If you've been to an American airport, I think they're popular in America.
In Shanghai,
You see it in Shanghai airport as well?
everywhere.
Oh really? It's common, yeah? So you can use this for people as well. You see, it's not like an X-ray because it doesn't It doesn't go all the way. It will be stopped if the person has like a gun or a knife or something. So it's kind of like a type of X-ray machine.
But why sometimes we can't put the computer together with the cell?
Why we can't?
We can't. We need to separate.
Yes. I think I don't know. Actually, I don't know. I just think it's because maybe sometimes people might try to hide something in the computer. No, I think so, maybe. So if you have the computer separate, so that the person can concentrate on the picture of just the computer, you know.
But what things we can't see?
What can't we see? I think we see most things except for maybe like some very light clothes, you know, like t-shirt. Because you know, gamma radiation will definitely go through my t-shirt, but maybe my skin will stop most of it. Like you can see here, you see this truck I'm picturing, the truck wall is probably only like this thick, so the gamma will go through it, but the machine gun will stop the gamma. You see it's black, it's very black. And like here you see the engine is very black because the engine is made of metal, a big piece of metal, so most of the gamma gets stopped here. But the window is nearly white, meaning the gamma mostly goes through the glass. I'd say something like solid steel, like in the machine gun or in the engine, would stop it. And also the rubber tires, you know, it looks like the two wheels are stopping most of the gamma. Yeah. So you see this airports, train stations, like this.
We have something can cover something cannot.
I think you just need lots of metal or lots of lead, you know, just something really thick. This is all. Yeah. Gamma will go through most things. Yeah. So you can just say cobalt 60. Its half-life is 5 years. So, you know, you can use the X-ray machine maybe for about 5 years. Cobalt 60 gives off lots of gamma radiation. This is what you want for this. In fact, I think 95% of the radiation from cobalt 60 is gamma. So you can just say gamma radiation from cobalt 60 can be used to look inside of machines, passengers, people, whatever. Yeah? Did you write something, Hugh?
Yeah.
What'd you write this time?
Yeah.
Wait, say that again, Yeah? Yeah? That's it? Using what? Using gamma radiation from cobalt 60. What did you write, Abraham? Yeah, okay. Next example. So this is actually, this one I was looking up today, boron 10. Boron 10 is actually not radioactive. It's not radioactive. So I think I should explain with a picture here. Of course, as you know, especially modern day life, cancer is a problem. So here is the person here. Well, this is their skin. So under their skin, they have some cancer. What you do is you put inside the cancer here, you put some, you know, the doctor comes along and the doctor gives a needle, and the needle puts inside here boron 10. That goes inside the, you know, the injected. Yeah? Then what they do, you see in the machine like this, this machine, now I don't know if the machine looks like this, but it'll be something like this. It fires neutrons at the person. So what you have here is you have neutrons, and they get fired at the person, and then they go through the skin, and they hit the boron. And then the boron turns into your boron 10, and you fire some neutrons at them, maybe like something like 2 neutrons, and it will become boron 12, for example. Now boron 12 is radioactive. So then what happens is this becomes radioactive. So what comes off of this? Alpha, beta, and gamma. In fact, most of the radiation that comes off of it is alpha. Now remember, alpha is very damaging, but because it's inside of this, it will damage the cancer. Also, what's very useful is the half-life here is equal to only 20 milliseconds. This means it decays very quickly, and so it doesn't hurt the good part, the healthy part of the person. Now this is a new treatment. I read about it today. Yeah, I was reading about it today. It's a new treatment. I think it's quite good because I saw this on an American website. I think they said something like maybe 10% of hospitals use this treatment. Now there's many different ways to do it, but what I like about this one is I think it's safer, because normally what happens is like this. You have your cancer here, and normally what they do is they send in gamma radiation from all different directions, and the gamma radiation, it all meets in this one spot and damages this. But I feel like this maybe isn't as safe, because you have all this gamma radiation coming in on one spot. So for example, maybe you damage some skin here. You know what I'm saying? Anyway, all I want you to say for this one is that something like boron 10 and neutrons together, you can use this to kill bad cells. And what I really like about this is that the half-life is nearly 0, so it very quickly decays and disappears. Yeah? You can use it to kill the cancer cells. Yeah. No, these treatments are usually just used to cut or destroy the cancer cells. Yeah. Kill them. Destroy the problem. Yeah. Yeah. So I mean, it's funny because you think about radiation as being very bad for your health, but as we can see here, we can have good uses for it. Yeah. Okay, we'll go to the next example. Oops. Now this one, we're back to cobalt 60, which we used for our machine at the airport, wasn't it? Wasn't it the airport machine? Yes. Now, cobalt 60 can be used by farmers. Yes, farmers. Sometimes when you buy an apple, sometimes the apple tastes bad. What do we call this? If the apple's too old, it doesn't taste right. Yeah, like it's soft or something. Yeah, what do we call this? There's a word in English. No? We don't know this? You eat the apple, but it's soft. It's not hard.
Not fresh.
Yeah, there's a word for that. ripe. You know this word? Not fresh. Not fresh will do. Now, what makes the apple become not fresh? What happens? Well, apple. On the outside of the apple, there's, bacteria. You know bacteria? Little bacteria. And this, is eating the apple, and the apple is getting old. So what you can do is you can put some radiation here, and you can kill the bacteria outside the apple. So this means the apple can last longer. Yeah? So that's one use. Also, when you're on a farm is very messy, dirty. So if you want to clean your apples, a lot of places, just put them in a big tub of water, and washes the apples. But you can use radiation to wash it, to kill all the germs on the apple. So you can see that it makes it last longer on the shelf. Also, insects like flies. If the fly lands on the apple and you use the radiation on the apple, what will happen to the fly? Yeah, like in Tusk, isn't it? You put gamma radiation on the fly and make it a superfly. So what would really happen with the gamma radiation on the fly? It won't become Tusk fly. What would happen to it? It will become a dead fly, yeah. And if the radiation doesn't kill the fly, something still happens to the fly. What happens to it? So the radiation might kill the fly, and if it doesn't kill the fly, something else will happen to the fly. Yeah, it damages it, but how? It damages it in a certain way. They're good, but it still flies. Not this.
It's not flies anymore?
It still flies, and it can still fly. Yeah. So the radiation will do two things. It will kill it, or it will make it infertile. Do you know what this means? Yeah, it cannot reproduce. No more little flies. Yeah? So this is why radiation is good for farmers, because it can kill the insects, and if it doesn't kill the insects, it will make the insects infertile, meaning they cannot make more insects. Yeah. Now, of course, the only problem with this is your apple now has gamma radiation on it. Yeah, well, what would happen is you would have your apples, and they would be going past on a machine. And here there would be some cobalt 60, just in a box. And the gamma radiation comes off the cobalt 60. So the apple goes under, and it just gets some gamma radiation. So it's clean, because remember, we said radiation is odorless, remember this? Tasteless, colorless, and what else do we say? You can't, odorless, colorless, tasteless, and inert. Chemically inert. It won't cause a chemical reaction. So this means the gamma radiation, you can't see it on the apple, you can't taste it, you can't smell it, and it doesn't change the chemistry of the apple. So again, this is another reason that makes it popular for our farmers.
The skin is porridge.
Yeah. This is because it's too old, too much bacteria on it. Because what happens is the bacteria eats the apple, and then,
So it's very fresh. The apple is very fresh, and inside the skin is then the porridge.
Soft? What do you mean? Porridge? What do you mean?
Tender.
Like porridge?
Sometimes you get the car is porridge can make the fresh.
Polish?
Yes, porridge.
On the apple?
Yeah.
I've never heard anyone do this. They put something on the apple to make it look fresh. Okay. I know in supermarkets, what they sometimes do is they put spray some water on the apples to make them look, shiny and fresh. Yeah, shiny and fresh. That's all I know. So in the supermarket they may come along and just go squirt, 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 and the apples look nice and shiny and fresh. Yeah, they do this a lot in America. I think it's only water, it's okay. Yeah, if you use something else, maybe it's not. But if it's only water, it's okay. Yeah? Okay. What else do we have? No. There's one more, which is what you need for the exam. So you can just say cobalt-60 is used by farmers to kill the germs and insects. Yeah, but how? Keep food fresh by killing germs. Got that? Okay. Now, here's the last one, although my picture's not so big. So, we're talking about carbon-14, and carbon-14, if you remember from the last class, is radioactive, and the half-life is about 5,000 years. And there's carbon-14 in everything that's alive. There's carbon-14 in all of us. Yeah? And how does the carbon-14 get inside of us? Well, this is what happens. There is, from the top of the atmosphere, there are some neutrons. Now, we'll talk about where the neutrons come from later, but right now there's just some neutrons at the top of the atmosphere. Now, the air we breathe is mostly made of what? What's in this air? Nitrogen, yeah? So the neutrons hit the nitrogen. How many protons in carbon? Not carbon. Sorry. Oh yeah, how many protons in carbon? 6. And how many in nitrogen? 7, isn't it? Or is it? 5. Or 5. Or 7. Check your table. Is it 5 or is it 7?
I'll go with 5.
I think I'll go with 5. We'll find out now. Unless I have my internet open. No, I don't. Nobody has their table. You think it's 5? I think it's 5. I think. Anyway, what happens here is the neutron hits the carbon. No, sorry. No, I need the periodic table. No, I think it's 7 now. Oh, no, I don't know. I'm terribly confused. Yeah. Where's nitrogen? Zoom in. Yeah. 7.
You're right.
He's right, of course. So you have your nitrogen with 7 protons. And then what happens is a neutron comes along and hits the nitrogen. And one of the protons leaves the nitrogen. So if the nitrogen has 7 protons and now it has 6, what does it become? It becomes carbon. It has 6 protons, yeah? So what you have in the air now, these neutrons hit the nitrogen, 1 proton is lost, and in fact it becomes carbon-14. So in the air there's carbon-14. Yeah? Carbon-14 goes into the plant. Because you know from biology, basic biology, the plants, they like to eat CO2. They like carbon. And then what do they make from the carbon? Oxygen, yeah. So the plants eat the carbon, and so the carbon-14 is inside the plants. Got that? Now, what eat plants? Well, animals maybe eat plants. So the carbon-14 that's in the plant is now in the plant and in the animal. And then we eat the animal, and so we now have the carbon-14 from the animal, which is from the plant.
We can only get carbon-14 by breathing the air.
I don't think so, because I think only plants can take the carbon-14 from the air. I think our lungs can only take the oxygen from the air. So the carbon goes in and then it comes back out. It doesn't get taken by the lungs, I think. Anyway, this is how the carbon-14 gets inside of it. So the carbon keeps going in. And then when we die, the carbon stops going in, because we stop eating. And then the carbon starts to decay, so the radiation starts to come off.
Can stay in the inside 5,000 years?
Yeah, after 5,000 years, half of the carbon-14 leaves your dead body. So for example, maybe Louise has, I don't know, 10 grams of carbon-14 inside of her. And then when she dies, she'll have 10 grams. But then 5,000 years later, her body will have 5 grams of carbon-14.
Actually, in the group or in where?
Everywhere, yeah. Every part of you has this, yeah. It's everywhere in your body. So, I mean, this is how we can know how old people are when we find them, you know, like caveman. Because you just need a small part, like their bone, and you can see how much carbon-14. So if they have only 5 grams of carbon-14, then how old is the body? 5,000 years. And if they have 2.5 grams of carbon-14, how old is the body? 10,000 years, yeah, 5 grams. No, got it. So the reason everything that's alive has carbon is because we eat animals, animals eat plants, and plants eat air. If I don't eat animals, if I only eat plants, I still get it. You know? So I think it's impossible. I don't know. Maybe there's one example of something that's alive that has no carbon-14 in it, but I don't think so. I think everything that's alive has carbon-14 in it. Because of this. So what you would need to do for the exam is they might say, explain how carbon-14 works, the data. Now you don't have to write a lot. I would say something like neutron. So before you write this is up. Neutron from the space hits the nitrogen in the air and turns it into carbon-14. The plants eat the carbon-14 in the air, the animals eat the plants, and the people eat the animals. So then we all have carbon-14 inside of us. And we can use carbon-14 to calculate the age of the person. Yeah. So write something like this, please. Oh, that's a terrible diagram. Now, you might ask me, where do the neutrons come from that hit the nitrogen in the air? That's a very complicated answer. So you just can say the neutrons come from space. But the true answer is actually very, very complicated.
say the carbon-14 can live on everybody for the...
I would say carbon-14 is in everything that is alive. So if you are alive, then you have carbon-14. Congratulations. Let's have a look here. Yeah, you can calculate the age. Yeah. So we all have the same amount of carbon in us because it comes from the air. Same amount. Per kilogram. Of course, I have more because I'm bigger than you. But per kilogram is the same amount. Yeah. Let's see. Does everything have C14 in it? I wonder if there's any examples of something with no C14 in it. Does everything that is alive have C14 in it? Oh, for goodness sake, it's not giving me anything useful. World of Warcraft. Yeah, sorry, I'm not getting anything useful here. Nothing useful at all. Alright. Except for... No, I can't find anything. So I'd say everything that's alive has carbon-14 in it. Yeah. Alright. Now, I don't know if there's time to do the question, but I would like you maybe to try a question. Let's see, a radiation question. Let's have a look here. Let me show you here. It's on page 11. Okay. What did you do with CSAP last time? Oh. What's the last physics CSAP you did? Which one?
We need to get a physical.
What did you do before that? Even we've gone very slow. There's an experiment I wanted to do with you, which is in this question. I think I'll ask them to do it next week. But basically, if you look here, this A part 1 is about the Rutherford experiment. Now, if he doesn't do it with you, I'll do it with you. It's a very simple experiment. But anyway, when do you get to see this week?
No.
Oh, for goodness sake.
And then last week also cancer.
That's a matter as well. Last week, okay, but not next week. Fine. So I'll have Stephen do the Rutherford one with you anyway. So anyway, you can start with part 2, which is describe an atom. So what's the part of an atom? Proton, neutron, electron, okay? give two properties of the strong nuclear force. Correct, yes?
Yes,
It's the strongest, yeah. B bar, one you have to balance this equation. Now this is alpha. So what's missing here for alpha? Helium 4-2. Yeah. So you need to balance it. Part 3 is they give you the half-life and they want to know the decay constant. So which formula do you use? T r lambda equals log 2. And then they give you a sample of radium and they give you the M0 and they want the activity, so the A. Then they want to know how many remain after 3 half-lives. So this is 1 half-life, so after 3 half-lives. So, after 1 half-life, what happens? It's half. Then after 2 half-lives, a quarter again, yeah. And then after 3 half-lives, 1/8. Yeah, so basically, you just need to divide this number by 8. Okay, you see it's not very difficult, is it? And then the last part is they want the time, and they give you the n. N equals M0, E, yeah. So, we have physics tomorrow and on Friday. So I think I would like you to do this one for me tonight. I don't think it will take you a long time. There's no graph to draw. If you like, I would like you to do this first, and then if you have time, please try to look at this on the internet. Now if you don't, okay, but I would like you to try and look up the Rutherford experiment. It's a very simple experiment using alpha radiation and gold. You know it? Maybe when you look at it, you recognize it. Anyway, I'll ask Stephen B to do this one with you next week. Because this one is actually popular in the exam. I think I've seen the answer maybe 4 times. Yeah, but then when you see it, you remember it, yeah? So page 11 is what I want you to do tonight. Yeah, the whole page, V5, yeah. So page 11, write that down. There's no time to do it now, but if there's time tomorrow, if you finish the class, if you finish the nuclear energy tomorrow, maybe with extra 10 minutes, I think it'll take 10 minutes to do it. I'll do it tomorrow. Okay? If I can't do it tomorrow, I'll just do it next week when we start our revision. But I want you to try it tonight, because we just finished radiation now, so everything you can remember is, yeah? All right, we'll leave it there.